Today I'll be working through some of the problems from the practice midterm for the Physics 455 midterm that's coming up here pretty quick. Specifically, I'll be working through all the questions and the solutions that Jason has posted online, and I'll be kind of working through the steps that I would take as a Physics 455 student when I did the midterm a couple years ago. So we'll start with question 1, and question 1 reads that the electric potential in a region of space is given by V is equal to K sine theta sine 2 phi. So we can right away write down V is K sine theta sine 2 phi, where K is constant with the right units. So that means that K is like the classic 1/4 pi epsilon naught. For our purposes, it doesn't really matter what K is, it's just some constant. And we want to find what is the electric field for this region of space. So the way I approach this problem is I first look at the potential and I think, okay, what is the potential dependent upon? So we see that V is a function of theta and phi. And this, to me, means that it's in spherical coordinates. For example, if V depended on Z and phi, we might think cylindrical coordinates, or if it was X and Y, we might think Cartesian coordinates. But this specifically kind of gets your mind thinking, what are the conditions on V, what are the coordinates, the system that V is in, and how should we kind of approach the problem using this coordinate system of choice. To find the electric field, we recall that E is equal to the negative gradient of our electric potential V. Now here is where our coordinate system comes into play, because we want to know what is the gradient of V in spherical coordinates. So from our formula sheet, we can see, that's on the back of the midterm, we can see that the gradient of V is simply dV by dr, r hat, plus 1 over r dV by d theta, theta hat, plus 1 over r sine theta dV by d phi, phi hat. I'll switch markers here because this one's kind of dying. And once again, this 1 over r and the 1 over r sine theta are kind of the scaling factors that come about with the gradient in spherical coordinates. So now we find that electric field is a negative gradient of our potential, and we simply plug in the potential into this equation, and we'll be able to find our electric field. So we'll start that up here. We see that E is equal to negative d by dr of our potential, so K sine theta sine 2 phi r hat, minus, again, the minus sign from in front of the gradient over here, negative 1 over r dV by d theta of K sine theta sine of 2 phi theta hat, and then finally 1 over r sine theta dV by d phi of K sine theta sine of 2 phi phi hat. So now we simply just need to take these derivatives in these coordinates, and that'll give us our electric field. So we find that the electric field E is equal to, this first term doesn't depend on r, so we have a 0, because the derivative of a constant is just 0. And then we have minus 1 over r. We can pull the constants out of this, which are K and sine of 2 phi. And then we take d by d theta of sine theta, which is just cosine of theta in the theta hat direction. And then we subtract off 1 over r sine theta. Again, the K and the sine theta come out this term as constants, and we have d by d phi of sine 2 phi, which gives us 2 cosine of 2 phi hat. We can do some canceling. The sine theta here cancels with that sine theta, pull a negative K over r out of the entire term, and we end up with the final electric field being negative K over r sine of 2 phi cosine of theta hat plus 2 cosine 2 phi hat. So once again, to kind of walk through the steps of how I thought about this, I saw the potential, I thought, what is the coordinate system that we'll be using? Theta and phi, spherical coordinates. We recalled that the electric field is equal to the negative gradient of the electric potential V. Here is the gradient of V in spherical coordinates. We plug in, we take our derivatives, and we end up with the electric field being negative K over r sine 2 phi cosine theta in theta hat direction plus 2 cos 2 phi in the phi hat direction. So now problem 2 for the midterm says, there's a solid sphere with a charge density that can be taken to be rho is equal to k over r. So right away we know that our charge density is equal to k over r. And while this approximation blows up at r equals 0, because if we have 1 over 0, that's equal to infinity, and this doesn't work, then that point can be safely ignored for this question. So we don't want to consider the point r is equal to 0, especially because this function isn't going to kind of work out there for us. So for part A, it says find the electric field E for the region R is less than A. So we start off with our sphere of charge, and the charge density on this is rho, which is a function of R, it's k over r. This has radius A. We want to find the electric field E for R less than A. So if you've been watching the videos on Gauss's law, you can remember that because of the spherical symmetry of our charge here, we can use a Gaussian surface centered at the same center of our charge distribution here with a radius of little r. And this will allow us to use Gauss's law to find the electric field in this region. So we recall that Gauss's law is the closed integral of the electric field dotted with the infinitesimal area element dA, and this is equal to the enclosed charge by our Gaussian surface over epsilon naught. Get my notes here. So again, we're going to exploit the symmetry of this charge distribution because it's spherical, use a spherical Gaussian surface inside, and this will allow us to use Gauss's law to find the electric field. If we start with the left-hand side of this equation, we can recognize that the electric field will be radial, and we have the closed integral of the electric field dotted with the infinitesimal area element. And from the other videos on Gauss's law that you can watch, you can remember that these two vectors are parallel at all points on the Gaussian surface. And what that means is that the dot product simply becomes multiplication of the two magnitudes. Now the electric field will be radial in all directions, will also be constant at every point on the Gaussian surface. So we can pull it outside of the integral. And we're left with simply the left-hand side of this equation becomes, draw a little arrow here, it becomes ER 4 pi r squared is equal to Q enclosed over epsilon naught, where our 4 pi r squared is the closed surface area integral of our Gaussian surface with radius r. So, change pens again because this is dying. We can now look at the right-hand side of this equation, and we have that the enclosed charge is equal to the triple integral, or the volume integral, from 0 to 2 pi, 0 to pi, and 0 to r. We integrate out to our Gaussian surface because we're only considering r less than a. And we want to take this integral of our density, and we're going to do this in spherical coordinates. So we have r squared sine theta dr d theta d phi. Now this will give us our enclosed charge by our Gaussian surface at some radius r. So right away we can see that the sine theta and the d theta and the d phi, there's no theta and phi dependence in our charge density, so we can just integrate those out. And remember that's equal to 4 pi, and then we have the integral from 0 to r of k over r prime squared dr prime. Now I'm using primed r's here just to kind of distinguish between the r of our integral here, but there's no difference. We can say that's any variable. The r prime is simply a notation to distinguish this r from that r. So we see that one of those r's each cancel, and we're left with 4 pi, the integral from 0 to r of k r dr with the primes, which is simply equal to 4 pi k r squared over 2, where again now this r is the radius of our Gaussian surface. Putting it all together, we have that ER 4 pi r squared is equal to 4 pi k r squared over 2 epsilon naught. Make sure we have that right here from Gauss's law. We do. So we can cancel the 4 pi r squared, cancel the 4 pi and the r squared, and we're left with the radial electric field, because again we know the electric field is radial, is equal to k over 2 epsilon naught r hat. Now we recognize that this is a constant field. For r is less than a. So again, what did I do? I started with writing down what is the charge density for this setup of this charge distribution. We say rho is equal to k over r. We recognize that this charge distribution depends on r and r alone, so we can think of spherical coordinates. We remember that using Gauss's law, when we have a spherical symmetry, we can use a spherical Gaussian surface to exploit the symmetry, use Gauss's law in its integral form, which is E dot dA is the enclosed charge over epsilon naught, solve through for what is the electric field on the left-hand side of this equation, which again, we can take advantage of the fact that ER and dA are two parallel vectors. This simplifies the dot product. We can pull ER out of the integral. And then we find what is the enclosed charge on the right-hand side using the volume integral of the charge density in spherical coordinates. Get some cancellations here, and we end up with the electric field is equal to k over 2 epsilon naught r hat. It's a constant field in the region r is less than a. So now we'll look at part B, and part B says find the electric field E for r is greater than a. So once again, we have our charge distribution with radius a has charge density rho is equal to k over r, and this time we'll be looking in the region r greater than a, so we draw our Gaussian surface radius r outside of our sphere of charge. Now this is very similar to part A, where we recall that we want to use the closed integral of the electric field dotted with dA, the infinitesimal area vector, is equal to q enclosed over epsilon naught, where this is Gauss's law in integral form, and that's how we're going to find the electric field outside of our sphere of charge with radius a, given the spherical symmetry of this distribution. So the only thing that's different in this case is the enclosed charge, because we're no longer inside of the sphere. So the left-hand side, we can just rewrite down from a is ER is equal to 4 pi r squared is equal to q enclosed over epsilon naught. So again, for the derivation of this side, watch the video on part A. But the enclosed charge will be different. And this time, again, we'll take the volume integral of the charge density in spherical coordinates, 0 to 2 pi, 0 to pi, 0. We take rho of r prime squared sine theta, dr prime, d theta, d phi. Now the only thing that's different than the case when we're inside the sphere is this boundary here. So before, when we were inside the sphere of charge at radius r, we integrated out from 0 to r. In this case, our Gaussian surface completely encloses the charge of the sphere, so we only integrate out from 0 to a, which is the radius of the sphere of charge. So we include all of the charge inside this q enclosed. Again, we do this integral, we can immediately take out the 4 pi, and we have the integral from 0 to a of k over r prime squared dr prime, which becomes 4 pi k, the integral from 0 to a of r prime dr prime, and we find that our enclosed charge by our Gaussian surface is 4 pi k a squared over 2. By taking this integral. Now plugging this all back into the equation for Gauss's law, we have ER is 4 pi r squared is equal to our enclosed charge 4 pi k a squared over 2 epsilon naught. Get some cancellations, the 4 pi's cancel on either side, and we're left with that the electric field is radial, and outside of the charge distribution is k a squared over 2 epsilon naught r squared r hat. K squared over 2 epsilon naught r squared r hat in the region r is greater than a. So once again, we used some of the information that we knew from part A, from already solving part A that makes it move faster. The enclosed charge is different in this case because the Gaussian surface is outside our sphere of charge. So we integrate out from 0 all the way to the radius a, gives us a different enclosed charge. Plug that into Gauss's law, and we end up with the electric field outside of the sphere of charge is ka squared over 2 epsilon naught r squared r hat. So for part 2c, we see that you can make E equal to 0 for r greater than b by adding a very thin, infinitely thin, spherical shell of charge at radius b. So here we have our initial charge distribution with the spherical sphere of charge, radius a. We put an infinitely thin shell of charge at radius b. That has the opposite charge to that of the inside in order to cancel and make the electric field equal to 0. In the figure that's shown on your midterm, the shells have the same center, so they're centered at the same point. And the question is, must the center of this new spherical shell be the same at the same center as the first spherical shell? And explain. So what that means, it's asking, is do these two spheres, this infinitely thin shell of charge and this sphere of charge inside, do they need to be centered at the same point, this point in the center here, in order for the electric field to be zero? And the answer is yes. But why? The answer is symmetry. So if we recall that Gauss's law is the closed integral of E dot dA, enclosed charge over epsilon naught. We can see that by if we put just a Gaussian surface all the way around here. Of course, anything flowing outside of this Gaussian surface will be the positive charge from this sphere of charge in the inside and the negative charge from the infinitely thin shell, and therefore the flux coming through the surface is always going to be equal to zero, regardless of whether or not they're centered on the same point. Again, that's because the flux from the positive sphere of charge on the inside and the flux from the equal and opposite negative infinitely thin shell of charge on the outside are going to cancel, and our Gaussian surface is going to enclose all that charge, and the charge through that surface is equal to zero. However, the electric field is only equal to zero if they're centered on the same point due to symmetry. If there's a slight offset, Gauss's law will not be the same for both of them, and there'll be some sort of slight charge discrepancy, charge distribution, based off the inconsistency of the symmetry of the two shells. Therefore, if we want the electric field, E, to be equal to zero in the region R is greater than B, these two charge distributions, the infinitely thin shell and the sphere of charge, need to be centered at the same spot and need to be concentric shells in order for the electric field to be equal to zero. For part D of problem 2, the question reads, write down the charge density rho for the spherical shell, which is the infinitely thin spherical shell that we were considering before. So because it's an infinitely thin shell, that makes me immediately think of a delta function. So we have the charge density rho is some constant, which we don't know, times the delta function of r minus b. And the reason here that it's r minus b is because we're looking at some position r in space, but b is the radius of the shell. So therefore, we're always offset by this radius b. So this is the charge density. Boom, done. Not really. We need to know what is this constant, c. That's what this problem is trying to get you to find. So we can do this by recalling that from part B of this problem, we had that the total charge, the total enclosed charge of the sphere of charge that's inside our infinitely thin shell was equal to 4 pi k a squared over 2. Just make sure I have that right. 4 pi k a squared over 2, yes. So this was the total charge that we found of that sphere of charge with charge density rho is equal to k over r in part B. And the reason we need this is because we want the infinitely thin shell to have the exact equal and opposite total charge in order to cancel out and make the electric field equal to zero. That means that the total charge on the shell is equal to negative 4 pi k a squared over 2, equal and opposite to that of the charge inside the shell. So we can now recall that the total charge is equal to the volume integral of the charge density. And then we're going to use spherical coordinates, so r squared sine theta dr d theta d phi. And now we integrate, we're going to go 0 to 2 pi in theta, 0 to pi in phi, and we'll go 0 to infinity. We'll include all of space for this charge distribution here. So by subbing in our charge density here, we say that we have 0 to 2 pi, 0 to pi, 0 to infinity of c delta r minus b, r squared sine theta r dr, sorry, just dr d theta d phi. Now this is the integral that we want to solve, and by doing this we can see that we'll actually end up with c on this side because we know that q total is negative 4 pi k a squared over 2. Solving this out, we have negative 4 pi k a squared over 2 is equal to 4 pi because our charge distribution doesn't depend on theta or phi, and we end up with a c pulled out as well 0 to infinity of r squared delta r minus b dr. Now recall that the integral of a delta function, negative infinity to infinity, of some function f of x delta x minus a dx is simply equal to that function at a. So this delta function essentially it shifts our integral in order to, from being at position x to being evaluated at position a. And the bounds in this case don't really matter as long as you are within the range that you're looking for. So our position b is in the range of 0 to infinity, therefore we can do this integral, and the bounds are kind of finicky with a delta function. So we solve through this problem here. We have the negative 4 pi ka squared over 2 is equal to 4 pi c, and we evaluate this function at r squared at position b, so we end up with just b squared. Now we can cancel out, and we end up with our constant c is equal to negative ka squared over 2b squared, which gives us our charge distribution rho is equal to negative ka squared over 2b squared delta r minus b. Now, conceptually, to me, this is the most challenging problem of the midterm because it deals with the integrals of the delta functions and requires you to remember that for an infinitely thin shell, we have to think right away delta function. For a point charge, an infinitely small point charge, think delta function. And our delta function here is offset to the radius b. So remember, because the infinitely thin shell is set at that radius b, we have to have the r minus b term in our delta function that moves the delta function. And we don't know what the constant is out front. That's what we need to find in this problem. Again, we remember from part b that the total charge on that sphere of charge inside of our infinitely thin shell, the positive charge, is 4 pi ka squared over 2, which means that the total charge on our shell needs to be equal and opposite in order for it to cancel out, negative 4 pi ka squared over 2. We do our integral, our volume integral, in our theta and phi space. We substitute in what we know, which is the q total, and we have to solve this integral using the delta function. Recall that the delta function simply pulls our function to be evaluated at the point that is shifted in the delta function. This allows us to find c. We can plug it in and find our charge distribution. So now we'll work through question 3. Question 3 reads, some region of space has a vector field, and we take the constants c1 through c8 to be constants with appropriate units, kind of like k from problem 1. None of the constants are equal to 0. And it says, which, if any, are possible electrostatic fields, and which, if any, are possible magnetostatic fields, and which, if any, are neither electrostatic nor magnetostatic, and you need to show how you know. So what we need to recall is that if we take the curl of some general vector field A, and this is equal to 0, this will give us an electrostatic field because the curl of an electrostatic field is equal to 0. And if we have the divergence of some vector field A is equal to 0, this will give us a magnetostatic field because, again, the divergence of B is equal to 0 for a magnetostatic field. So these are the two things we need to remember in order to distinguish whether or not it's electrostatic, magnetostatic. So part A gives you some vector field A1 is equal to C1 Z x hat. Now the trick to this problem is we need to take the curl and we need to take the divergence of every single one of the vector fields that Jason's given you. And we need to first think about what is the coordinate system that we want to do this in. This first one requires z and x, therefore we should think Cartesian. So we'll start with the divergence. So the divergence of A1 is equal to dA1x by dx x hat. Sorry, it's not x hat because the x hat's incorporated in the x. So again, for the divergence, we take the divergence of first the x component with respect to x, and then we take the divergence of the y component with respect to y, and we take the divergence of the z component with respect to z. And this is the z, x, and y components of our vector field here. So the x component is of course c1z. So we take d by dx of of c1z plus, well, there is no y component, so that's 0, plus there is also no z component, that's also 0. And of course, d by dx of c1z, this is all just a constant, so this entire divergence is equal to 0. So therefore, the divergence of A1 is equal to 0, and this means that this could be magnetostatic. Next, we need to check the curl. So we take the curl of A1, and this, again, you can use the formulas from your formula sheet, but this says we take d by A1z by dy minus d of A1y by dz in the x hat direction. And we add d of ax by dz minus d of az by dx in the y hat direction. And then we add d of a, these are all a1, which is just the vector field we're considering now, d of a1 y by dx minus d of a1 x by dy in the z hat direction. So lots of these will be 0. Of course, there is no z direction and there is no y direction, so it's simply 0 x hat plus the x hat direction is here, so we have d by dz of a1x, which is c1z, minus 0 because there is no z component, y hat, plus again 0 z hat because there is no y. Sorry, it's not 0 here. It's 0 minus d by dy of c1z, which of course that derivative is 0 because there's no y dependence here. So we end up with the curl of a1 is 0 x hat plus c1 y hat plus 0 z hat, which does not equal 0. So this field can be magnetostatic, but it cannot be electrostatic because we need to have that the curl of a vector field is equal to 0 in order for it to be electrostatic. So again, we have the divergence of A1 is equal to 0, and the curl is equal to C1 y hat. So now for part B, we have our vector field A2 is equal to C2 S hat plus C3 over S phi hat plus C4 Z hat. And again, we want to find whether or not this vector field is electrostatic or magnetostatic. So we'll start with divergence. And when I look at this problem, I look and I see we have S hat, phi hat, and Z hat, so I think cylindrical coordinates. So now we have to take the divergence in cylindrical coordinates, which again, take from your formula sheet, we have 1 over S d by ds of S as plus 1 over S dA phi by d phi plus d az by dz, where as, a phi, and az are the respective components of the vector field C2, C3 over S, and C4. By plugging those in, we have 1 over S d by ds of S times C2 plus 1 over S d by d phi of C3 over S plus d by dz of C4. So we'll see that this right away is 0, this right away is 0 because they're constants with respect to these variables. However, we have 1 over S C2 from the first component. So therefore the divergence of A2 is equal to C2 over S is not equal to 0. So this is not magnetostatic. Now we check the curl. We say that the curl of A2, again in cylindrical coordinates, is some big long expression from your formula sheet, 1 over S dAz by d phi minus dA phi by dz S hat plus 1 over S d by ds of S a phi minus dAs by d phi z hat, and I missed a term in the middle, but we can add that in now. We have dAs by dz minus dAz by ds phi hat. So again, we have our S hat, our Z hat, and our phi hat. I wrote them in the wrong order, but they're all there. So we substitute in our values for AS, A phi, and AZ, and we end up with 1 over S dAz by d phi. So right away we can see that the AZ component doesn't depend on phi, so that's going to be equal to 0. And we have dA phi by dz. Again, the phi component doesn't depend on z, so that's also 0. Some simplifications rather than having to write out all the steps. Now we look here and we see that the A phi component contains C3 and an S, so the S and the S will cancel, and then we take the derivative of a constant, so that's also equal to 0, with the 1 over S out front, right here. And we have the AS component doesn't depend on phi, so that's also equal to 0, z hat. And the final component, AS with dz, and there's no z component in our S hat direction, so that's also equal to 0. And we have AZ by ds, which we look at our z hat component, there's also no S there, this is also equal to 0. So what this means is that the entire curl of A2 is equal to 0. Again, you can write them out explicitly and add in your AZ, your A phi, your A phi, your AS, your AS, and your AZ, and that will kind of give you one more step here. But in order to save space, I didn't do that. You can do it on your own practice midterm just to prove to yourself that each of these components is in fact 0. On the midterm itself, if you want to save time, save space, you don't necessarily have to write that step, but if you want to make sure you get it right, I would recommend writing out that extra step just to make sure that you get the math right and the derivatives right, and don't forget anything like the 1 over S here or the S inside from the formula sheet. Anyways, the solution to that is that this is equal to 0, which gives us that this is an electrostatic field. So we have that the vector field A2 is not magnetostatic, but it is electrostatic. So the vector field for part C is A3 is equal to C5 R phi hat, which I look at this, I see R, I see phi hat, I think spherical coordinates. Again, electrostatic, magnetostatic, we need the curl on the divergence. We start with the divergence of A3 in spherical coordinates. Again, take that from your formula sheet. We have 1 over r squared d by dr of r squared a sub r plus 1 over r sine theta d by d theta of sine theta a theta, all that in brackets here. And then we have plus 1 over r sine theta dA phi by d phi. So there is no r hat component, so this first term is 0 because AR is equal to 0. There is also no theta hat component, so A theta is equal to 0, so that second term is also equal to 0. So we simply have 1 over r sine theta d by d phi of C5 r phi hat. Of course, C5 and r are constants with respect to phi, so this is all equal to 0. And the divergence of A3 is equal to 0, and this is a magnetostatic field. Check the curl. Again, we'll have some long, complicated expression in spherical coordinates. So we have 1 over r sine theta, big bracket, d by d theta, sine theta, a phi, minus dA theta by d phi, all r hat. We will add 1 over r, in big bracket, 1 over sine theta, dAr by d phi. This may look daunting, but this is simply the formula from your formula sheet, so just plug and chug. I'm just writing it down so that you can see the steps. R a phi, big bracket, theta hat, and then plus 1 over r d by dr, r a theta, minus dAr by d theta phi hat. Now, if we look in this first term, we have a phi here, so we have the curl is equal to 1 over r sine theta. This first bracket here is d by d theta of sine theta a phi, which gives us C5 r. And now right away, I'm going to stop. I'm going to look at this expression. I'm going to think, holy man, I don't want to plug in all those problems. I only have 50 minutes to the midterm. I'm already crunched for time. I'm on problem 3. There's 10 minutes left. What am I doing? I'm gonna look at this. I'm gonna think a phi is c5r. And we have a sine theta with a derivative with respect to theta. D by d theta of sine theta is cos theta. Cos theta does not equal 0. This means that right away, we automatically have a component that is not equal to 0. We can check this briefly with saying minus d by d phi of the a theta component, which is 0, so it's simply minus 0. So this cos theta is not going to cancel with anything. And we can see that right away, this curl of a3 does not equal 0 because the cosine theta does not equal 0. So if at home you want to test it for yourself and make sure and plug in every single one of these terms, take the derivatives and prove it to yourself that yes, this in fact does not equal 0. Get the terms, that's awesome. But Jason is not asking for that in the problem. He's asking, does it equal 0? Here right away we see, no, it does not equal 0. Save yourself some time, save yourself some space, save yourself some stress. This does not equal 0. Automatically not electrostatic. Now personally, I would probably solve through and prove it to myself because I work in steps and incremental steps, and mathematically I can see that yes, I need to plug this in, plug this in, take the derivatives. So personally, I would write it all out step by step. Here, I already ran out of room. So here it's not really the most conducive for me to be able to explain it to you and fill up this, and it gets confusing with the board being full. But if you want to take a shortcut, recognizing right away that this is not equal to 0 saves you a ton of time, ton of stress, ton of mistakes, because if you plug in all these variables here, there's so much room for error, so many places that you can take a derivative wrong, you can plug in a value wrong, you can read this expression wrong. By simply recognizing right away that this derivative does not equal 0, the curl does not equal 0, this is not electrostatic, but yes, from the divergence, it is magnetostatic. So part D of problem 3 says, for a vector field that is a possible electrostatic field in parts A through C, find the charge density rho for the electrostatic field. If there's more than one, pick one that you prefer. If there isn't one, then you can use the expression he has here for an electric field in order to find rho. He's just asking you to see if you can manipulate a formula in order to find the charge density rho. So we recall that the divergence of the electric field is equal to rho over epsilon naught for an electrostatic field. Now the electrostatic field that we found was in part B. I'll just find it here in my notes. That field was A2 is equal to C2 S hat plus C3 over S phi hat plus C4 Z hat. So we found that in part B, the divergence of A2 was equal to, we should take the solution here right away, it's just C2 over S. So if you watch part B of this video, then you'll be able to see where this comes from. But we're only looking for the charge density rho. So if we rearrange the formula above, we can see that rho is equal to epsilon naught times the divergence of the electric field. In this case, our electric field is our electrostatic field, A2. So simply we plug this in, we have that rho is equal to epsilon naught, divergence of A2 to C2 over S. And there's your charge density. Now Jason has also given you an electric field in case you didn't find the first one, so I'll work that through here as well. We have that E is equal to 2C6 R hat plus C7 R sine theta theta hat plus C8 R sine theta phi hat. And again, we find the divergence of E is equal to rho over epsilon naught. So if we want to find the charge density rho, we can take the divergence of this in spherical coordinates. So again, we get the big ugly formula, 1 over r squared d by dr of r squared er plus 1 over r sine theta d by d theta sine theta e theta plus 1 over r sine theta d e phi by d phi. And we take these derivatives, we have 1 over r squared d by dr of r squared 2c6 plus 1 over r sine theta d by d theta sine squared theta sine theta, another sine theta above, C7r, and then plus 1 over r sine theta d e phi by d phi, which is C8 d by d phi of C8 r sine theta phi. Take these derivatives, stuff will cancel, and we'll end up, I'll just write the result here. The divergence of E is equal to 4c6 over r plus 2c7 cosine of theta plus c8. So then when we get our charge density rho is epsilon naught times the divergence of E, and we find that rho is equal to epsilon naught times all of this, 4c6 over r plus 2c7 cosine of theta plus c8. Now I didn't take these derivatives explicitly because of space on the board, but we can quickly check through that these work out. So we plug ER into here, it's just 2c6, and we have the d by dr of r squared times 2 times c6. The 2 and the c6 are constants, we pull them out. The derivative of r squared is 2 times r. The r will cancel with the r, and we're left with 1 over r times 2 is 4 times c6. That's that component here. You can write it out yourself at home, test it out. That's this derivative. D by d theta of sine squared theta C7r. C7 and r are constants with respect to theta. We can pull them outside of the derivative. The r and the r will cancel, and we get the derivative of sine squared theta, which using the chain rule is 2 sine theta cosine theta. The sine theta cancels with the sine theta. We're left with 2c7 times cosine of theta. And finally, the last derivative is 1 over r sine theta, d by d phi, this ugly term here with its respect to phi. The phi goes away, the rest are constants, we pull them outside the derivative, and we end up with the r sine theta canceling, and we end up with just c8. So of course, this divergence here is ugly, and this divergence here we already found in part B. So hopefully, if you're able to find what is this divergence in this electrostatic field from part B, you can simply use the result right away, and you don't have to do this whole derivative again. Either way, you'll find out that the charge density rho is equal to the divergence of the electric field, or whatever electrostatic field we have, times constant epsilon naught. So for now, for problem 4a, it says each of the 7 points on a heptagon has a charge of equal magnitude. The distance between the center and any point on the heptagon is h. The origin is at the center of the heptagon, right here, and the y-axis points straight up from the origin to the top of the charge. So we have that our y hat is up. Part A says if all 7 of the charges are positive and have a charge q, so I've written positive q for each of these 7 charges, what is the electric field at the center of the heptagon? Now, in lecture, Jason did a very similar problem with a pentagon of 5 sides, and we can use Coulomb's law in this case where we take Coulomb's law for each of these charges and we take the superposition principle and we add up all the vectors and we cancel some stuff, and there's lots of vectors and there's lots of math and lots of angles, and what's the angle, this interior angle for a heptagon? Who knows? It's really challenging and really complicated. By a simple symmetry argument, we can find what is the electric field at the center. If we look at this heptagon and we take the 7 charges and we rotate the heptagon by 2 pi over 7 degrees, and that's, 2 pi over 7 radians, 2 pi over 7. And the reason I did that is because there's 7 charges, 360 degrees, or 2 pi radians in the circle. We rotate by the exact angle in order to have the charge distribution be exactly equal once we've rotated it. So say this is Q1, this is Q2. After rotation, this will be Q2, this will be Q3, etc., if we rotate it all around. However, the charge distribution will be the exact same, which means that the electric field must also be the exact same. So that restricts the electric field at that center. Similarly, there's also a symmetry argument in terms of flipping the charge distribution. If we take this charge distribution and we simply flip it on its center so that now instead of facing you, the back is facing you, because this charge and this charge have the same magnitude, that means that it will also be the exact same charge distribution. So by symmetry, we have the same charge distribution, should be the exact same electric field. The only way this is possible is if in the one case the electric field is, say, pointing towards me, and we flip it, the electric field would then have to be pointing away from me. But if it's the exact same electric field, this is impossible unless that electric field is equal to 0. So by symmetry, and of course we love symmetry in all of our electromagnetic problems. By symmetry, the electric field at the center must be equal to 0. For part B of this problem, we had the exact same charge distribution set up with our heptagon. Everything's all centered on this origin here at a distance h. There's a distance h between each of these points. However, here we have that on the top there's a positive charge at 0h0 position, and it's positive q, and every other charge in this distribution is now negative q. So we think, wow, this is really hard. Now we have to use Coulomb's law again, add all the vectors, more math, but we can simplify this problem by recognizing the fact that before we had a distribution of 7 positive charges. Here we had a distribution of 7 negative charges, the exact same. The electric field at center should be 0, but we have simply taken a positive charge of magnitude 2q and placed it on top of that negative charge at the top. And due to superposition, again, the cancellation of a positive and a negative should give you 0, and a positive charge will be left over on top if we take the magnitude of positive 2q. So this setup is the exact same as in part A, except every single one of these charges is negative, and we have simply taken a charge of positive magnitude positive 2 and placed it on top of that negative charge at the top in order to have the exact same setup as if we had only that charge of positive 2q a distance h from the center. It's the exact same setup as in part A, but now we have simply taken a positive charge, positive 2q, put it at that position 0, h0, and we want to find out what is the electric field now from this charge alone. So we don't need to consider the entire charge distribution, just this positive charge of 2q. In class, Jason did a very similar problem where he had the fact that you removed that charge. In that case, it was simply like the same as adding only a charge of magnitude of equal and opposite magnitude. Here, because we have a positive charge at the top, we need to include a magnitude of 2q, which is in order to cancel the charge and then add an additional charge on top. Now we can use Coulomb's law, which says that the electric field is equal to 1 over 4 pi epsilon naught q over r squared r hat, where now this r squared, this r is the vector from our position of interest to our charge, which is simply h in this case. So we say that E is equal to 1 over 4 pi epsilon naught. Our charge is positive 2q. Our distance is h squared, and our vector, if we take the electric field at this point of a positive charge, is pointing away from the charge in the negative y hat direction, because electric fields point away from positive charges. This will be in the negative y hat direction. So the electric field of this heptagon charge distribution is 1 over 4 pi epsilon naught negative 2q over h squared in the y hat direction. Again, negative because it points away from that charge, positive 2q, has a magnitude of positive 2q. H squared is our r vector, distance between the charge and our region of interest. And we just have to remember the fact that we initially had a charge distribution of 7 negative charges, and we have simply placed a magnitude positive 2q charge on top in order to simulate as if we had that positive q on top. So question 5, the final question of the practice midterm, probably the quickest math-wise if you are able to understand the concept that's asking for. So it says a rectangular box with a square cross-section contains a part of a very long line of uniform charge density lambda. So here we have our box, the uniform line of charge density lambda passing through the center. So the length of the box is h, the cross-section is a square with sides of length a, and the line of charge runs down the center of the box. So that line, the line of charge runs down the center of the box, is probably the most important of the problem. What that means is that this line of charge is centered perfectly inside of this rectangle, or this rectangular prism, and that means that it's symmetrical in the center compared to all 4 sides. Now, it says find the electric flux phi e through one side of the box. Through one side of the box. Now recall that the electric flux phi of E is equal to the amount of charge enclosed by some surface, in this case our rectangular prism, over epsilon naught. And the flux through any surface enclosing the charge is the amount of charge inside the surface. So the electric field that's flowing out from this line of charge is going to pierce the surface of this rectangle. In this case, it's only going to pierce the 4 long sides that include the H and the A, because the electric field flows out radially, so it's not going to be flowing along either end. There's no electric field moving this way, there's no electric field moving this way, so it's only going to pierce the 1, 2, 3, 4 sides, and it's going to be flowing out away from the line of charge. And the enclosed charge here is simply the length of the rectangle, H, times the uniform charge density lambda. So this lambda is the charge density per unit length of this line of charge, and we have that it passes through the rectangle for a distance of h, therefore h times lambda gives us our enclosed charge by the surface here. So we take phi of E is equal to h times lambda over epsilon naught. Now Jason was asking for what is the electric flux through one side of the box. Now this box of course has 6 sides. There is no electric field flowing through either end of the box. Now we're down to 4 sides. And because the line of charge is centered specifically and symmetrically at the very center of this rectangle, that means that the amount of flux flowing through each of the 4 surfaces will be equal. So this here is our total flux, but the flux through one side is going to be h times lambda over 4 epsilon naught. And we divide it by 4 because there are 4 sides and the electric field will be moving through each side with equal magnitude because that line of charge is centered inside that rectangle. So again, 2 lines of math, but you have to conceptually understand that this line of charge passes through the very center of this rectangle symmetrically on all 4 sides. There is no electric flux passing through either end because of how the electric field flows off of this line of charge. The enclosed charge is h times lambda, and we have to divide by our 4, which is our 4 sides, in order to get the flux on one side of this rectangle. And that concludes the practice midterm for the Physics 455 midterm that you guys will be having in a couple weeks.